Hey everyone, in this video we're going to go over chapter 4.6, modeling with exponential functions. So suppose we start with a single bacteria which divides every hour. So after 1 hour we have 2 bacteria. After 2 hours we have 2 squared equals 4. 3 hours we have 2 cubed equals 8, and so on. So we could model the bacteria population after t hours by f of t equals 2t. So we have a base 2 here in this case because we're doubling every hour basically from what we have, and it grows off of each other. So this is exponential growth with time doubling. So if the initial size of a population is n naught and the doubling time is a, then the size of the population at time t is n of t equals n naught to t over a. So where a and t are measured in the same time units, so they're both going to be in minutes, hours, days, years, etc. So for example, we have a certain bacterial population doubles every 3 hours. Initially, there are 1,000 bacteria in a colony. So we want to find a model for the bacteria population after t hours. So we have our n of t, which our n naught is the initial size, which is 1,000. So we have 1,000, 2 because it's a doubling exponential growth model, and then t over 3 because our a is the doubling time. It doubles at every 3 hours. And then our part B is how many bacteria are in the colony after 15 hours. So we want to plug in 15 for our t. So we have n of 15 equals 1,000 times 2 to the 15 divided by 3. And that's going to be 32,000 when we plug it into a calculator. So we have 32,000 bacteria in the colony after 15 hours. After how many hours will the bacteria count reach 100,000? So we have our n of t equals 100,000. So I set that equal to 1,000 times 2 to the t over 3. And I'm going to solve for t. So I just divide each side by 1,000. And I get 100 equals 2 t over 3. I could take the log, the common log of both sides in order to cancel out my base 2 basically. But it doesn't cancel it, but we're basically trying to get the exponent down. So I have log of 100 equals log 2t over 3. Now we know log of 100 is 2 because I have basically log, let me write it on this side. I have log of 100 of 10 equals some power. So we know 10 squared equals 100. So that's why it's 2. So I have 2 equals, and then I bring the exponent to the front. So I have t over 3 log 2. And I divide by log 2. And then I multiply by 3. And I get 6 over log 2, which is approximately 19.93. So about 20 hours, the bacteria count will reach 100,000. Okay, my next example is a new breed of rabbit was introduced to Cambria 8 months ago. The current rabbit population is estimated to be 4,100, and it doubles every 3 months. So we have 4,100, 8 months ago, doubles every 3 months. What is the initial size of the population? So our doubling time is a equal 3 in months. And then our population at time t is going to be n of t equals n naught to t over 3. So we want to solve for n naught. So our initial population that's n naught. I need to make this capital P. So our population is 4,100 when t equals 8 months. So that's our current. So I could plug in 8 months and then let our n of t be 4,100 to solve for n naught. So I have 4,100 equals n naught to 8 over 3, because n of 8 is 4,100. So I have n naught equals 4,100 over 2 to the 8 thirds. And that's approximately 645. So that's the initial size of the rabbit population. So now we want to estimate the population 1 year after the rabbits were introduced. So we know that n naught equals 645. So we have n of t equals 645. 2 to t over 3. So after 1 year, that's going to be t equals 12. So I plug in 12 for our t. So I have n of 12 equals 645 to 12 over 3, which is 10,320, so approximately 10,000 rabbits. So that's going to be after a year. So here I have a sketch of the graph, and it's just the one that the book provided. You could do it using Desmos or your graphing calculator. It's a pretty big window. And then note that our t is going to be greater than or equal to 0 because it's time. So that's our graph. So it goes up pretty quickly, as you can see. All right, now I'm going to go over exponential growth, relative growth rate. So before we used a function with base 2 to model the population growth in terms of doubling time. We could really use any base. So we could do base 3 for tripling time. We could really model with any base. We usually use base E in terms of relative growth rate R. So the rate of population growth expressed as a proportion of population at any time. So we could see that our exponential growth rate is n of t equals n naught e r to the t. So nt is our population at time t. N naught is the initial size of the population. Our relative rate of growth is a proportion of the population, that's r. And then t is time. So here it's just a naught is the same thing as n naught. But I want to show the growth versus decay factor. So if k is greater than 0, the function models a growth. And if k is less than 0, then the function models a decay. So we could see the differences in the graph with exponential growth and exponential decay. We have basically a positive slope versus like a negative slope, basically. Alright, so in this example, I have the initial bacteria count in a culture is 500. Our relative growth rate is 40% per hour. So we want to find a function that models the bacteria after t hours. So our n naught is 500 and our r is 0.4 because that's our relative growth rate and our initial. So I have n of t equals 500 e to the 0.4 t. So what is the estimated count after 10 hours? So we could plug in 10 for our t, and I have n of 10 equals 500 e to the 0.4 times 10. So I have 500 e to the 4, which is approximately 27,300. After how many hours will bacteria count reach 80,000? So I have n of t is 80,000. That's like my population after a certain time. So I want to solve for the t. So I have 80,000 equals 500 e to the 0.4 t. So I divide by 500 to both sides. I get 160 equals e to the 0.4 t. And then I could take the natural log because our base is e. So I have natural log of 160, and then the natural log of e to the 0.4 t. These cancel, and then I'm left with 0.4 t. So I have t equals natural log of 160, and I could divide by 0.4, which is approximately 12.7 hours. So after that many hours, the bacteria count will reach 80,000. Alright, our next example is in 2000, the population of the world was 6.1 billion. So that's our initial count. The relative rate of growth was 1.4% per year. It's claimed that a rate of 1% per year would make a significant difference in the total population in just a few decades. Test this claim by estimating the population of the world in the year 2050 using a relative rate of growth of 1.4% per year and 1% per year. And then we want to graph them and compare them. Okay, so for our first part, we have 1.4. So in decimal, 1.4 is 0.014. And I have n of t equals, and our initial is 6.1. And our n of t is going to be in billions. So I basically have 6.1 billion. And then e is 0.014 t, and t is in years since 2000. Alright, and then, so 2050 is 50 years after 2000. So I have my n of 50 equals 6.1 e 0.014 times 50. So that's 6.1 e to the 0.7, which is approximately 12.3 billion. So that's the population with 1.4% per year. And then with 1%, that's going to be 0.01 in a decimal. So I have n of 50. We're using the same time here. 6.1 e to the 0.01 times 50 is 6.1 e to the 0.5, which is approximately 10.1 billion. So they're pretty, there's a pretty big significant difference here of about 2 billion. So when we graph them, you could see that the one with the 0.014, it's a little bit steeper than the other graph, but not by too much. Okay, so now we have a radioactive decay example. So radioactive substances decay by spontaneously emitting radiation. The rate of decay proportional to the mass of the substance, basically. Rate of decay is in terms of half-life. So it's the time it takes for a sample to decay to half of its original mass. So a radioactive substance with mass m0 and half-life h, the amount remaining after time t, is modeled by m of t equals m0 to negative t over h. And that's because it's decreasing. So we want to express this in the form m of t equals m0 e r to the t. So we need to find our relative decay rate r. So I'm going to go ahead and start with m of t equals m0 e negative rt. So I can, basically we're going to, our m of t is m0 over 2 because we're, the half-life rate of decay is when you have your original and then you go to half of that. So our m of t after a half-life, basically, we're going to have half the original mass. And then our m0 stays the same, and then alright, so basically we could replace the t with h because h is the half-life or the time it takes for the sample to decay to half of its original mass. And then I could cancel out the m0s. I get 1/2 equals e to the negative r h. And then I could take the natural log of both sides to cancel out the exponential. So I get natural log of 1/2 equals negative r to the h. Log of 1/2 equals, and then the natural log cancels out the e on the other side. So I have negative r to the h. I divide by h, so I have natural log 1/2 divided by h equals negative r. But then when I divide by negative 1, we could basically move the negative 1 to the ln 1/2 and make it to the negative 1 power, which would mean that this equals natural log of 2. So then I get R equals natural log 2 over H. So here's the radioactive decay model. So if M naught is the initial mass of a radioactive substance with half-life H, then the mass remaining at time t is modeled by M of t equals M naught E negative RT, where R is natural log of 2 over H, which is the relative decay rate. Okay, so for example, we have polonium-210 has a half-life of 148 days. Suppose a sample of the substance has a mass of 300 milligrams. We want to find a function M of t equals M naught 2 negative t over H that models the mass remaining after t days. So I have M naught equals 300. I'm going to write this a little bit clearer. Okay, so our M naught is 300. Our H is 140. That's the half-life. So I have M of t equals 300 times 2 negative t over 140. Now we want to find a function M of t equals M naught e to the negative RT that models mass remaining after t days. So I have M naught equals 300. R is the natural log 2 over 140 because 140 is our half-life. And then that's approximately equal to negative 0.00495 RlN 2 over 140. So our M of t is 300 e to the negative 0.0495 t. Oh, actually, I think I forgot a 0 there. Yeah. Forgot an extra 0. So we want to find the mass remaining after 1 year. So we're going to use the part A function. So I have t equals 365 because that's a year. So I have 365 days, M equals 300e negative 0.00495 times 365, which is approximately 49 milligrams. So that's the mass remaining after a year. How long will it take the sample to decay to a mass of 200 milligrams? So I'm going to use part B with M of t equals 200. So I have 300e negative 0.00495 t equals 200. I divide by 300, and I get e to the negative that t equals 2/3. And I take the natural log of both sides to cancel out the e. So I get negative 0.00495 t equals natural log of 2/3. So I have t equals negative natural log of 2/3 over 0.00495, which is approximately 82 days. So when I graph the sample mass as a function of time, so in part C, I used the part A function, and part D, I used the part B function. However, you could use the model in part A or B, the two different functions, whichever one, they're going to be the same. They're going to give you the same result. So if you use different ones for that, you're going to get the same, and then the graphs are also identical. So here's a graph on the left. So either one works, but okay, now we have Newton's law of cooling. So this law is talking about the temperature of a heated object. It decreases exponentially over time to the temperature of the surrounding medium. So this is something that you could see in your everyday life with just when you're cooking and things are cooling. So we have the temperature T of a heated object at time T is given by T of T equals C, where C is the constant temperature of the surrounding medium, T naught is the initial temperature of the heating object, and K is a negative constant that is associated with the cooling object. So this is a little bit different formula than the one the book gives. It's the same, it's just the variables are different, but I like these variables better. So, and then the KT is just, remember, it's a negative KT. Okay, so for example, we have a cup of coffee. Coffee has a temperature of 200 degrees Fahrenheit. The book has really, really hot coffee and is placed in a room that has a temperature of 70 degrees. So after 10 minutes, the temperature of the coffee is 150 degrees Fahrenheit. So you want to find a function that models the temperature of the coffee at time t. So our first part is I'm going to find T naught minus C. So our T naught is 200. And then our C is the room temperature. So 200 minus 70 equals 130. So I have T of T equals C, which is 70, plus 130 e to the negative kt. So we want to find k. So we know when T equals 10, the coffee temperature is 150. So T of 10 equals 150. So I could plug those in. So I have 70 plus 130e negative 10k equals 150. So I have 130e negative 10k equals 80 by subtracting 70. I divide by 130. And then I could take the natural log of both sides here. So I basically cancel out the e. So I get negative 10k, and then I have natural log 8 over 13. I divide by negative 10. I get k equals negative 1 over 10 natural log 8 over 13, which is approximately 0.04855. So our T of T is 70 plus 130e, negative 0.04855T. So now we want to find the temperature of the coffee after 15 minutes. So I just plug in 15 for T, and that's approximately 133 degrees Fahrenheit. And then we want to find after how long will the coffee have cooled to 100 degrees Fahrenheit. So we have T of T equals 100, and we want to find our T. So I have 100 equals 70 plus 130e to negative 0.04855T. So I subtract 70 and I get 30. And then I divide by 130. I get 3 over 13 equals e to the negative 0.04855t. I take the natural log of both sides, and the e cancels, so I have t equals natural log 3 over 13 over negative 0.04855, which is approximately 30.2. So it's going to cool to 100 degrees after half an hour. And then we graph, and so you could see here that our graph is approaching T equals 70, and that's our horizontal asymptote. So our horizontal asymptote is basically where it doesn't cross. So it's 70 because we're guaranteed to have the coffee get to 70 degrees. And basically, once it reaches room temperature, it doesn't get any colder than what room temperature is. I'm sure, like in the scientific world, there are fluctuations in the temperature, so that might change, and it depends like where the coffee is. But for our purposes, it's just going to stay to 70 because that's the constant room temperature, and the air is not going to be extracting heat from the coffee anymore because they've reached a stagnant temperature. And then I included the logistic growth model. Your guys' book didn't, but we did talk about this at some point when I had the COVID example and modeling how many people would get the virus, and with the equation that the book gave with disease. So I just want to provide that for you guys. It's pretty useful, but the book didn't talk about it. So that's it for this video. So I'll see you guys in the next one.